course, all the different paradigms between indoor and outdoor and so forth. Okay, so those are the goals. How are we going to do this? We're going to start with the OFDM family of waveforms. There's a lot of reasons that we do that. You can get to wider bandwidth with efficient receivers, good resistance to multipath. You can add filtering and windowing to tailor it to different emissions requirements or make changes that allow efficient operation at very high SNR. We're going to use that as the basis for this. And there'll be a common flexible framework, which I'll show you a little bit more detail, that's going to allow the, first of all, forward compatibility, the different types of multicast traffic, the different types of reliability traffic, and then advanced wireless technologies such as massive MIMO, and how are we going to use mmWave even outdoors to make this actually deployable. Okay, so I kind of just mentioned that. The OFDM family is what we're basing all this on. There are a couple of non-orthogonal waveform constructs, such as the resource spread multiple access, that are part of this. They allow, for example, an IoT device to transmit in an asynchronous manner without a grant. There's both single carrier and multi-carrier versions of this. If you wanted to get down to the really low cost, really low power PA, single carrier, high, good peak to average properties. So that's going to be part of the mix as well. And this is just a depiction of the scale. So on this diagram, you can see different subcarrier spacing. You can see different definitions from sub-gigahertz up to traditional cellular around 3 gigahertz, 5 gigahertz. You can see there's 160 megahertz chunks. So right now, let's just drill into that one a little bit. If you compare today's 4G LTE with the Wi-Fi family in that band, the way to achieve the very wide bandwidth with today's 4G LTE is through carrier aggregation. And if you make a receiver that's wide using that method, it works just fine. The performance is very good, but the cost there's an extra cost delta for that. So by defining these flexible spacings and being able to drop down 160 at once, or even wider for the mmWave, we can produce efficient designs that are very cost competitive, all the way up to 28 gigahertz, actually 60 gigahertz, maybe 72 gigahertz, and that's what we're trying to do. Okay, so this is a lovely diagram. Along the x-axis is time. On the kind of y-axis there is the frequency bands or the tones, and you can see first of all scalable TTI, transmission time interval. That's sort of the unit of time and amount of data that's delivered to the radio layer. And by having that very small, you can reduce latency. You can have fast turnaround. By having it longer, maybe you can get some more performance for flows that can tolerate that. LTE is already defined down to a millisecond. In 5G, we're talking about defining to maybe a fraction of a millisecond, maybe 200 microseconds, and be able to scale that. You can see in there in time a section for WAN, another section for multicast and peer-to-peer. Another section for blank, both blank in time and code. That means that's the ability to forward define some new waveform constructs that may be developed in the future and have them fit back into the same paradigm. Also the ability to puncture in high reliability transmissions, so when they have to go out for a critical application, the construct will support that. Okay, so now this picture shows many of the things that I was talking about all together in one. And as we look at this picture, let's kind of start in the center there. You see like a normal base station right in the middle. And coming off of that to the lower left is multicast. If I wanted to send you all the slides from this presentation in this room, I'd really want to do it with multicast. There would be enormous gains. In fact, the amount of network or capacity that I need to send to all of you is about the same as it takes to send to, say, two of you with the unicast method. So if more than two need the same data, I can give it to everyone with multicast at the same cost and capacity. So we definitely want to have that paradigm. Recently I was in the NOC at Akamai, and I saw internet traffic, and one of the biggest spikes that happens in internet traffic is the day that new iOS releases come out. And that's an example where a huge number of users are downloading exactly the same information, and that is a big spike, and that you could really do a lot with multicast. If you go to the upper left from that center base station, you see integrated access and backhaul. So with that, the concept is to use the same system, and even the same channels in many cases, to connect another base station, as well as to connect phones accessing the network. That's very cost effective for an operator. So we want to support that paradigm for sure. Now maybe the two base stations are going to use a higher order of MIMO. They may have relays and other options, but it's unified. Then it gets to the hyperdense. So on the left there, you can see hyperdense with self-configuration. I mentioned the test we're doing with many thousands per square kilometer density. We've come a long way in terms of self-configuration and base stations that can sense other base stations. And in this case, they're showing coordinated spatial techniques in the cases where you have the backhaul to do that and the timing requirement, you can get very, very high performance. If I go to the right, you see it's labeled massive MIMO, which is a term we use when the order gets above, say, 8 or 10. And I'll show you some results in a second. That gives you the ability to deploy 5G at, say, 4 gigahertz or 6 gigahertz and still use the same sites and same PA powers that you did for your existing deployment. We want to be able to do the low latency for the reasons I mentioned. On the bottom right is vehicle to vehicle or vehicle to X, meaning vehicle to vehicle, vehicle to pedestrian, vehicle to infrastructure. That's a peer-to-peer. And then, of course, the IoT with the low power and narrowband modes. Okay, so here's the comment about massive MIMO at 4 gigahertz. On this chart, this is a CDF of throughput, and you can see these comparisons. The one on the left is 2x4 at 20 megahertz channel at 2 gigahertz. The next one is 2x4, 80 megahertz at 4 gigahertz. And the last one is what we call massive MIMO, 24x4. And you can see that even at the cell edge, let's say the 5% or 10% point, that you're getting significant gain in throughput. And so if we define these modes and we can implement them efficiently in silicon, it has huge impact to the operator because now they can deploy these 5G paradigms on their existing cell sites. In this particular one, it was a 1.7 kilometer intercell distance and 46 dB transmit power. But that's sort of becomes very important as we start to look at these different bands and the operators want to reuse their sites. Okay, let's talk about millimeter wave. In the past, you'd think of millimeter wave as, okay, I'm going to use that to connect my phone to a display that's in the same room, or my set-top box, or for docking of a laptop. I wouldn't use it outdoors in a mobile environment. That would be crazy. It's not crazy. The picture there is from our 802.11ad technology, which is the 60 gigahertz Wi-Fi, and that little green thing, it's about half the size of a postage stamp, has 32 antennas on it. They're little dipoles. You can see them there around the outside. They form beams on both sides of the link. The access point forms beams. There's many reflections, and if you can pair them up, you end up with a very nice channel actually that has good properties. It may only last for a short amount of time, so you have to use it in an opportunistic manner, but the properties of it in terms of the presence of multipath and whatnot are actually very good. And so if you can use that channel, you can get tremendous throughput because there's a lot of spectrum, and you can fit these antennas in a small space, and so it's very exciting.
Now, the picture on the right is a result from Manhattan, which is kind of harkens back to the beginning of Qualcomm when in '89, it was before my time there, but in '89, the first CDMA demonstration was done in Manhattan. And one of the challenges there was to do handoffs when you come around a corner and you see a strong pilot coming into view very quickly and you have to hand off to it. Again, you can see from the colors on here, those same kind of challenges, but now we're at millimeter wave, and you actually can get, you're going to have large numbers of small base stations, but you can get this remarkable performance. Now, the industry is going to have to work hard. I mean, it's going to take years of research to get efficiencies of super wideband PAs and receivers and costs to improve. But we're starting, again, a 10-year cycle, and it's going to happen. These are some actual test results. The millimeter wave projects done by our New Jersey team. And the takeaway from this, if you look at the two pictures there, the two traces, one's at 2.9 and one's at 29 gigahertz. The takeaway is, notice it's not just attenuation. The actual shape of those results is very different. The relative height of the main path and the path that comes off multipath is very, very different. It's not just a scaling of attenuation. And secondly, the overall path loss exponent is comparable. So with the higher bands, you can make use of reflections and multipath, which happens much more often. It reflects off of many more things, and you can make use of that. It's a blessing and a curse. You can make use of it, but also you have to make use of it in order to work. But it's very promising, and these are some early test results on channel measurements. We've done an extensive set of channel measurements. One more comment on that. The way it's likely to end up is you're not going to have a 28 gigahertz device that does no other bands and expect to be able to carry like a voice call. You're going to have a device that has a ladder of bands, 28, 5, 2.4, sub-gigahertz, and you opportunistically use the highest one available. When you got it, you can go very fast, very quickly switch to the next one down when the top one is not available, and you make very scarce resource, sparse use of the scarce resource, sub-gigahertz. And in 5G, again, we talk about a unified approach. The MAC layer will be common. So that will facilitate carrier aggregation across these different bands and better handoff, and we'll be able to actually make use of them in that manner. Okay. We're still working on 4G. So I want to make sure that's emphasized. The 5G is going to take off, 2020 like we described. But in the meantime, you can see all this list of topics that we're adding to 4G. More and more sophisticated versions of carrier aggregation, peer-to-peer, massive MIMO, unlicensed. I'm going to talk a little bit about unlicensed. So that is in no way stopping. We're going full bore on that, and that's going to continue for the foreseeable future. Even today, with the great progress that operators have made to provide 4G coverage, it's still true that less than 10% of the smartphones in the world are 4G capable. They're being produced at a higher percent than that, but it takes time. So right now, that's the case. It's less than 10%. Basically, the story is there's a long way to go yet on 4G, and we're not stopping on that. We're continuing to work on that. And to that end, there's this new terminology called LTE Advanced Pro. Kind of reminds me of the iPad Pro. And you can see what's in that. More versions of carrier aggregation. We're evolving the LTE Direct capability. We're adding different types of vehicle-to-vehicle. So LTE Direct allows devices to discover each other at low power, and it does so around every 4 seconds. It listens, and you can leave that on 24 hours a day. The impact is comparable to a standby time, so it's almost nothing in a 24-hour period. You can leave it on all the time, but it's 4 seconds. So that's not suitable for vehicle to vehicle for safety applications, but we can take that design, we can reduce the latency and define it as V2V. So that's an example of one of the things we're doing as part of this improved LTE Advanced. Okay, and then another big one, is what can we do for IoT? So the first thing is we can define so-called Cat 0, where it's still a 20 megahertz channel, although the data rates are lowered and the device is simplified a little bit, and it can fit in the same network, and you can have machine type communication with basically a low-end LTE device. Then there's LTE M, which is narrower, a megahertz. The more narrow we get, we can have lower costs and more efficient PAs and receivers, and also reduce the number of bands to lower the cost. And now recently, industry's kind of come together for narrowband IoT, all the way down to 200 kilohertz. And now we can meet these requirements where you have a sensor with a battery, and it can last many, many years, still sending data several times a day for many, many years on that battery. So all the applications, utilities, wearable devices, all those things are going to be candidates for this kind of technology. Okay, I'm going to talk a little bit more about V2V and V2X. It just turns out, if you look at this picture, it probably wasn't intended, but this picture is actually a diagram of one of the accident scenarios that's actually, unfortunately, quite common. If you look at that picture there and see the way those vehicles are, imagine someone crossing the street from the bottom to the top of that diagram. And imagine the kind of white car is slowing and it's almost at a stop, but the other one is moving fast. The person walks up from the bottom, looks both ways, but the top left car is blocked because of the close car, doesn't see it, walks in front, and there's an accident. And that is the kind of scenario where there's at least the potential to improve it with V to P and V to X. We've done tests of this. It does work quite well. It is very challenging to reduce the false alarms, but it's something that you want low latency. You want a robust receiver that can work at Doppler. It has to be able to get around some blockages. You need very careful integration with user interfaces and so forth. But the potential for these kinds of things is really tremendous to increase safety. This is also showing the ability to connect to the light meter, the traffic lights and those things, again, to reduce traffic and improve safety. We believe that, I can't remember the exact statistic, but by 2018, something like 60% of produced vehicles will be so-called connected, and the regulators around the world are working to require these kinds of capabilities in all vehicles, and so there's a lot of potential with that. Okay, unlicensed spectrum. So again, going back to the core reason for doing all this is there's more, for our business, all of us here, there's more applications, more services, more content. We need to get the most use out of the radio spectrum that we can. And that's why we've studied using LTE in the unlicensed spectrum. Now, there are these families of technology in the licensed and the unlicensed. And by the way, Qualcomm is involved in both of them, and we care about them both very, very much. They are on a convergence path. And I think in some years, maybe around the 5G timeframe, you'll no longer have like two separate modem chips. You'll have one common core, and maybe there'll be some small hardware accelerations, but it'll be one common block with different ports, and it can operate in these different modes. And right now, the different families have different pros and cons. If you want an access point in your family room, you want very high performance, you want low cost, you go buy a Wi-Fi access point. The modern ones are tremendous. You can't really beat that. If you want to stitch together large numbers of stations to create a wide area network, and you want properties like predictable performance across vendors and robust mobility through handoffs and formality of specification, you want those things, then the cellular family has a lot to offer. And so we consider using the cellular family of technologies, in particular LTE, on these bands. Now, why didn't we do this on 3G? Well, there wasn't really, with one exception perhaps, TDD, widespread 3G technologies to which to put in the unlicensed bands, which are mostly unpaired spectrum. With LTE, of course, that's not the case. There is TD-LTE. So in this paradigm, we use the carrier aggregation concept with a licensed anchor, and then you can add on extra carriers in the unlicensed band. And we also then consider taking that licensed anchor and moving it into the unlicensed band, with some changes, of course, to create an entirely standalone unlicensed version of what is now known as LTE. And when we do that, we have to change the LTE. And this is like a very important message that I want everyone to understand. This is not vanilla, unmodified LTE. We've made very critical changes to it in order to promote coexistence with Wi-Fi. We have to do the carrier sensing and algorithms to share the channel, and we have done exactly that, and I'm going to show you some test results. Okay, so in this picture, on the upper left, you can see the part of the setup there. You can see a whole bunch of antennas. We've got a very extreme setup with many different access points, all in a small area. They're inside an RF screen room, and we did these tests to see what would happen to Wi-Fi users in the presence of LTE unlicensed users. And you see these 4 different blobs of stuff on the chart. The purple stuff is the average throughput of the Wi-Fi users. And we start on the left with basically 8 Wi-Fi users, and then as we go to the right, we gradually replace one at a time with an LTE user, until at the end, you have one Wi-Fi user completely surrounded by LTE users. And you can see the trend. The result is really everyone wins. If I'm communicating with all of you in this room with wireless technologies, say a whole family of them, and I take any one of them and replace it with something that's more efficient, everyone benefits. Not just the one you replace, but everyone else too, because you get off the channel a little bit faster. And that's exactly what's happening here. The more you go along this line, the better the performance is for everyone. Okay, and I think this is my last slide. Just kind of summarizing. We talk about solving the 1000x. This is what I meant when you looked at the extreme cases of the sports venues, the fact that we need, people are using 4K videos, and in the future, devices are likely to go beyond that in both directions, both consuming content, authoring content. There's going to be all these new services, so we really need 1,000 times more capacity on the network, because we don't want the data plan prices to go up. Actually, we